CITS Pre-Calc Section 4.3 is on logarithmic functions and their applications. Now logs are where a lot of students start to struggle a little bit, just because they have trouble understanding that logs are just the inverses of exponential functions. Okay, so logarithms and exponential functions are inverses of each other. So let's give ourselves a definition. If x is greater than 0 and b is a positive constant, then y equals log base b of x if and only if b to the y equals x. I know that can sound confusing, but all it's telling us is that if we have an exponential function where x equals b to the y, we can change that into a logarithmic function by sliding it over. Okay, now we've done this before. We usually slide this underneath, and I get y equals, this becomes a base, log base b of x. Okay, so part of what we'll be doing in this section is changing from logarithmic form to exponential form, and back from exponential form to logarithmic form. Okay, so if I'm going to change this one back to exponential, all I do is take this b, slide it over, and I get b to the y, I drop the log, equals x. Okay, that's all it's doing, just changing them back and forth. Now a big part of what we do here is make sure that you can say these things right. This is read log base b of x. Okay, because our base can change, so we have to designate what that base is, whether it's log base 2, log base 5, log base 27. We do have a couple of shortcuts. If it's a common log, the common log is always base 10. So I don't have to write the log in there. I can write it like this, and that assumes base 10. Okay? Or I can say the common log of x, which is also the way of saying base 10. We then have the natural log. The natural log assumes that we are in base e. Okay? So with the natural log, a lot of people say ln x. I don't like that because it just isn't right. It's the natural log of x. Okay? So try not to say, let's take the ln of each side. Because I had a student ln at one point and she didn't like that. So let's go with the natural log of x, the common log of x, or log base b of x. Now, if we have an exponential form or function of the form y equals log base b of x, again, if we're switching that around, I slide the b over, and that gives me b to the y equals x. If we're in logarithmic form, I slide the b over, the y drops down, and I put a log in front of it to change it to logarithmic form. Okay, and you'll get practice on the assignments of doing that, although I know we did a lot of it back in Algebra 2. We have some basic log properties. The most basic ones for our simplification process: if I have a log base b of b, that equals 1. Reason is, if I slide that b over, I get b equals b to the 1. And therefore, this is called my b to the x, so x has to be 1. Okay, so that value is 1. Log base b of 1 is 0, because anything to the 0 power is 1. Log base b of b to the x equals x. Okay, and we're going to come up with another rule later on, but if I look at this, I get b to the x equals b to the x, so x equals x. And the one that most forget, if I have b raised to a power of the log base b of x, okay, that's also going to be x. Easy way to remember it is these two are going to cancel off, and I'm just going to get x. And in class, if you wish, I will show you how to go ahead and prove that out. Now, our general properties for the log of x. For our logarithm function, we know the domain and the range. Now, remember the logarithmic function is the inverse of the exponential function. We graphed exponential functions before, just in the previous sections. Exponential function of f of x equals b to the x goes up to the right. Okay, goes to the point 0, 1, has a horizontal asymptote there at 0. Okay, and that's when b is greater than 1. We know that that exponential function had a domain of negative infinity to positive infinity, and a range from 0 to infinity. Well, what I'm telling you is that these are inverses of each other. If they're inverses, the domain becomes the range, and the range becomes the domain. So, being the inverse of f of x equals b to the x is f of x equals log base b of x. The domain of the exponential function now becomes the range of the log, and the range of the exponent now becomes the domain of the log. Okay? And oops, I should have that open. It's not from 0. So now, if I have that open, because it's open over there, and because I can't touch that line. If I look at the graphs are always go across the line y equals x. So I have my exponential function here. Here's my y equals x. And here is my graph of the logarithmic function. Okay, and we'll graph a log function when I start showing the examples here. But all we do again is we just start picking values of the power of that base. And we're able to graph that fairly quickly. Now, the tougher one to see is if b is a decreasing function. If b is decreasing, we know it goes down to the right. Okay, this red one here is my decreasing function. But when I flip that across that line y equals x, my 0, 1 becomes 1, 0. Everything else also changes. But now it looks like this. It's coming down to the right. Okay, I said down to the left earlier, I think. I think it went down to the right. They both look like they're going down to the right. It just looks like it's transposed, but it is actually flipped over. Okay? So, and again, my domain and range will swap with that. Now, a couple of examples here. I picked out number 10 out of your book, and I was looking at it, and the book actually has it written wrong. The book actually had negative 3 equals log base 4 of 64, which is not correct. It should be negative 3 equals log base 4 of 1/64. Okay? So, if I've got, I want to write this in exponential form. Just like we did in the directions, I'm going to take this 4, I'm going to slide it over there. So I get 4 to the negative 3 equals, I drop the log, 1/64. That is now exponential form. Okay? If I want to write something in logarithmic form, 2 to the 5th equals 32. I take the base, and I slide it across the equal sign. The 5 drops down. I have to put a log in, because my base is 2, and that's of 32. Okay, real quick and easy, but what it does for us is if I didn't know what this was, if I had x equals log base 4 of 1/64, I can solve that by changing to exponential and then trying to get like bases. I know 4 to the x, I know 64 is 4 cubed, so therefore 4 to the x equals 4 to the negative 3, so therefore x is negative 3. That's where they get the value of that logarithm. Okay, the next two are going to actually do that with us. So they want us to solve out log base 8 of 1/512. Now, a lot of people can do these in their heads. When they look at it, you realize that this has to be the same. If we're not going to use a calculator, there has to be some way of getting this base into the same units as what I'm taking that log of. The easy way to do it is set it equal to something. Then change it to exponential form. So I have 1/512 equals 8 to the x. So now I need to get both of these into the same base. Well, when I was doing this the first time, I looked at it and said, well, I don't see 8 being a part of 512. But I know 8 is 2 cubed. So on this side I have 2 to the 3x. I know 512 is 2 to the 9th. So therefore this is 2 to the negative 9 because I have to bring it up top. Now my bases are the same, so I can set 3x equal to negative 9. Therefore x is negative 3. So log base 8 of 1/512 is equal to negative 3. Now if you do see it and know that, I'm open that here, that 512 is 8 cubed, it's a little bit faster, but we do get the same answer. Number 38 is quite a bit tougher because I've got a decimal and then I've got a fraction. And you start looking at it thinking, what the heck do I do? Well, they have to be compatible. So I looked at 0.3 and went, well, 0.3 I know is 3/10. Now I'll take that and set it equal to x. When I do that, I slide the 3/10 over. I get 100 over 9 equals 3/10 to the x. Well, I need to get these somehow the same. I know 109, that's the same as 10/3 squared. And now they're the same, they're just reciprocals of each other. So I'm going to go flip that over and say 3/10 to the negative 2 is 3/10 to the x. Therefore, x equals negative 2. And the value of this function then, or of that logarithm, is negative 2. Now, when you take them without a calculator like these problems are, you got to be real careful to make sure you get like bases and then just set the exponents equal to each other. Couple more problems. 50, we're going to go ahead and graph this log. Now, in the book it says graph the log by using the exponents. So let's do it their way first. I'm going to go y equals log base 8 of x. And I'm going to push that over, and I'm going to have 8 to the y equals x. So when I make my xy table, I'm going to go with y equaling 0. So x is going to be 1. If y equals 1, x is going to be 8. And if y equals negative 1, x is going to be 1/8. Okay, so let's take a look at where that graph's at for us. If I've got 1, 0, there's 1, 0. I've got 8, 1. And I've got 1/8, negative 1. I'm really tight to there. Now, is there any way that this x could ever be a negative? No, there's not, because that y value is an integer and 8 is not negative. So I can't get a negative. So that's where I get my horizontal or vertical asymptote there. And I have my graph of the function. And that should have been up a little bit, but we're okay. Okay, so they just changed it to exponential form and then started picking values of y. Okay, I like to do it like this. I just start picking values of x that are powers of 8. So if x is 1, okay, or I'm sorry, if x is 8, y is 1. If x is 1, it's 0, and if x is 1/8, then that value would have to be negative 1. It's whatever way you want to do it. It doesn't really make much of a difference to me. But the big thing is we've got our graph here. We don't have to do a whole lot of labeling with it because I've got the coordinates. Again, I like coordinates in an XY table off on the side of the graph, not actually on the graph itself. It's easier to see stuff. Let's take a look at the domain. The domain, okay, is going to go from 0 to infinity because I've got my vertical asymptote there, and my range from negative to positive infinity. Okay. Find the domain of the function. Well, if I'm looking at domain, the big things you have to remember is that when I'm taking the log of something, it has to be greater than 0. Okay, I can't take the log of 0, and I can't take a log of a negative. So when I'm taking the log of something, whatever is in here has to be greater than 0. When we were doing domain, we were teaching it, I said you always start with a domain of negative infinity to positive infinity, and then take out what doesn't work. Okay? So my domain starts here. Is there any number that I plug in here that's going to cause that to be negative? Okay, well, when I square it, it's going to be positive no matter what it is. Add 1 to it, it's always going to be positive. So the domain of this one really doesn't change. Okay, it's going to be all real numbers, negative infinity to positive infinity. Okay? Now you're wondering, why is it different here than here? It's because of that squared. Okay? It's going to give you a little bit of a different graph there. The second one, if I'm looking at this, again, it has to be greater than 0. Well, inside here is a parabola. So what I do is I factor that. So I've got x plus 5 and x plus 2. Well, if I think about how the graph looks, okay, now what people will make a mistake on this one is right away they'll say, well, x can't be negative 5 and x can't be negative 2. So they'll give me this domain. Negative infinity to negative 5, negative 5 to negative 2, and negative 2 to infinity. Because we've been able to do that so far because our graphs were continuous. But if I look at the graph of this, okay, and just using this as my line, and I've got negative 5 and negative 2, my parabola looks like this. Well, these are the values where it's positive. These are the values where it's negative. Well, we can't have a negative value in with a logarithm there. So let's check one of those. Let's check when x is negative 3. Okay, that's between these two. If x is negative 3, I get 9 minus 21 plus 10, which is negative 2. Can I take the log base 7 of negative 2? No, I can't, because it has to be greater than 0. So by thinking of the graph, I'm able to look at this and go, oh, these don't work. So my actual domain for this is negative infinity to negative 5 and negative 2 to infinity. So you need to be careful about just looking and seeing, well, okay, it's where it equals 0. It's not. Those are the breaks, but I have to look at each individual area and make sure that they work also. Okay, so there's section 4.3. We'll work on questions tomorrow.